Can I start?
Yeah, please go ahead.
Okay. Good afternoon, everybody. So my name is Associate Professor T.S. Dr. Sachin Sharma, and I am representing Taylor's University School of Engineering, Malaysia, as well as Lincoln University College School of Engineering, Malaysia. And today I will be presenting about the enhancement of barrier protection of organic coatings with the incorporation of graphene oxide nanomaterials as a reinforcing filler. So this will be my presentation outline, where I will be discussing about the problem statement, literature review about the topic, research objectives, experimental materials and methods, results and discussion, and conclusion. So as we all know, in the past decades, corrosion has been a serious threat to both society and economy. And there has been, it was reported in the past that the annual costs resulted from the degradation of metal or steel substrates were approximately 2.2 trillion. In other words, affecting 3% of the world's annual gross domestic product, GDP. So in order to address this issue globally, researchers have devoted significant efforts towards the development of new corrosion prevention strategies. So figure 1, as we can see, actually illustrates the steel corrosion process that occurs in the presence of water, oxygen, and electrolyte ions. So the whole purpose over here is to actually apply smart coatings or multi-layered coatings in order to delay the corrosion process or to delay the penetration of the electrolyte ions to reach the metal substrate interface. This is because corrosion cannot be prevented fully. However, we can only delay the process of corrosion. So this will be very effective because we can actually lessen, okay, the cost resulted due to the corrosion, which degrades the substrates such as metals and etc. for various applications like construction, pipelines, and etc. So the next slide. So the literature reviews, I'll give a little bit of background of what were the efforts on developing corrosion prevention strategies such as barrier protection, anodic and cathodic protection, active corrosion inhibition, self-healing, the incorporation of inhibitors such as metal oxides like TiO2, zinc oxide, graphene-based nanomaterials, and etc. So this were the figure 2 illustrates the concepts of corrosion protection strategies, and figure 3 illustrates graphene-based materials, why they are being used and how they are being widely used in various applications due to their fascinating properties such as high electrical conductivity, high fracture toughness, very high Young's modulus, good electron acceptor, good surface morphology, chemical inertness, large surface area, approximately 2630 meter squared per G, high energy barrier, and etc. So why graphene? So graphene is actually a single molecule crystalline structure held together by carbon atoms, which forms hexagonal honeycomb lattice with the sp squared hybridized bonds. So it has an electronic configuration of 1s squared, 2s squared, and 2p squared, thus making graphene the strongest and hardest possible material today. Moreover, graphene is also the mother of all other carbon electrodes, as illustrated in figure 4. And we can see over here in figure 5, graphene, many sheets of graphene forms a graphite, which has a lateral dimension of 0.33 nanometer. However, a single sheet of graphene has a lateral dimension of 0.142 nanometer. And nanometer dimensions are very much favorable for various applications, as we all know that nanotechnology has advanced significantly over the years. So the smaller the size of the particle, the better it is. Why? Because if you look at graphene itself, we look at the energy band gap structure of graphene, the valence band is actually touching with the electron band is touching with the valence band. So which means that the point where they touch is called a direct point, DIRAC, which means that they have to receive very minimal energy or maybe no energy for the electrons to transfer from the valence band to the conduction band. Okay, so that's the reason to why graphene is a very fascinating material and it has extremely high electrical conductivity. So if we, for example, we scatter graphene nanoparticles on a filter paper, and we just take a roller and apply and just roll it on the surface of the filter sheet, by receiving little energy or little heat from the rolling process, manual rolling process, they get excited and they get closely packed to each other. And when that happens, the electrical conductivity increases. So what's the research objective of this study? Is actually to develop acrylic epoxy-based polymer composite coatings, nanocomposite coatings with superior barrier properties by the incorporation of graphene oxide nanofillers, GO. And then we also want to identify the optimum loading ratio, the size of the nanoparticles, basically how the size of the nanoparticles affect the performance of the corrosion, and the type of coating system that are intact, and whether do they have multifunctional features. So I'll also explain why multifunctional coatings are much better than traditional coatings or conventional coatings. So the overall performance of the fabricated nanocomposite coating systems, they were characterized using 4 methods: water contact angle, WCA; number 2, electrochemical impedance spectroscopy; number 3, cross-hatch test according to ASTM D3359 standards; and number 4, field emission scanning electron microscope to actually identify the surface morphology of the coatings. So experimental methods and materials. So how do we actually fabricate graphene oxide? Okay, so in the past, I'm very sure everybody is very well aware of the hummus method. However, in my research, I have actually developed my own method, which is in the process of being patented. And I used a different set of methods, approach to get the graphene oxide. And interestingly, it also exhibited similar results as per the GO that was fabricated by the hummus method. So we can see in figure 7 illustrates the overall fabrication process of the graphene oxide. So I used 4 basic steps over here, which is functionalization, neutralization, filtration, and the drying process. So what was done at the initial stage was to measure certain amounts of graphene, for example, 1 gram or 2 gram, and with respect to the amount that was weighed, we add sulfuric acid, nitric acid, and potassium hydroxide in the ratio of 2:1 to 1, and we stir it at room temperature for 4 hours at 500 revolutions per minute. And after that it was done, it was then, that's called the functionalization process. So once the functionalization process was done, then we need to do neutralization and filtration. So basically we filter using high quality filter paper under the influence of vacuum. And the influence of vacuum plays an important role because it needs to segregate completely between the nanoparticles with the acidic solution. So if you do not use the vacuum influence, then your results would not be good because there will be large particles which will be left on the surface of the filter paper, and also it will be slightly wet. So it will not dry, and hence there'll be some kind of cluster, and that will be not good because when we want to do the blending process with the resins, it will not homogeneously disperse. So the neutralization, the filtration was done about 7 to 8 times. So let me explain what is being done first. So when we filter and separate the functionalized graphene oxide with the acidic solution, we use a clean spatula and we scrape out very, very carefully from the filter paper, and we place it into a beaker filled with water, okay, filtered water or deionized water. And then we stir it again at room temperature, and this process will be repeated for 7 to 8 times until we get a neutral pH, which means we have to bring the pH from pH 2 acidic to pH 7 neutral. So once that is done, the final neutralization process will be done for 24 hours. And this is because we want to make sure that the nanoparticles are dispersed evenly, and it will break down the clusters into fine nanoparticle size. So when that's done, after 24 hours, it is then filtered with a new filter paper, and then the neutral graphene oxide nanoparticles are scraped gently, and then it is placed on a Pedri dish where it is being dried in an oven at 80 degrees C for about 12 hours. Okay, 12 hours. And then the final product, it can be seen. It's when we scrape it gently, and that's the nanoparticles that we obtain or we yield at the end of the drying process. So for the composition over here, we used acrylic and epoxy. That is because we wanted to keep it consistent in terms of 90 to 10 ratio. And the graphene oxide that was incorporated into the coating systems had an increment loading rates of 0.5 up to 3 weight percentage. We kept the polydimethyl siloxane
नहीं नहीं मैं आज करता हूँ
consistent.
अभी तो एक ऑनलाइन एक मीटिंग चालू है मैं आज करता हूँ मैं 7 बजे तक नहीं नहीं अभी कैसा अभी वर्चुअल मीटिंग चालू है ना इसलिए हम अभी
Rahul ji, please mute your mic.
हो yes yes
Okay,
Sorry,
thank you.
Sachin, but we didn't see your presentation.
Pardon?
In my screen, I don't see your presentation, but presentation Professor Yeong, yeah?
Actually, Sachin, we are
Yeah?
not actually seeing your presentation. Dr. Dai Yen Yong, the presentation actually seen from that area, and it is only on the first slide. So your presentation is not here. So please unshare and then share your presentation again.
Okay.
But it's strange because I can't see this properly.
Me too.
Okay.
I can see it properly, the presentation.
Yes,
see
this
my
is yours.
slides now?
Yeah, this is yours. Yeah.
Okay. So can I continue from where I stopped, please?
Yes, I think so.
Okay.
Yes, now it's okay. Thank you.
Okay. So this was the geofabrication that I had talked about earlier, and this is a newly invented method by myself, and it's in the process of being patented. And now this is where I stopped. So this is the table 1 illustrates the compositions of the coating systems that were prepared along with its corresponding designation. So in this approach, I used acrylic resin and epoxy resin. So there are 2 types of resins over here in the ratio of 90 to 10 weight percentage. And this was kept consistent for all the sample preparation. So the only thing that was varied in this experiment was the inclusion of the graphene oxide nanoparticles in the increment of 0.5 up to 3 weight percentage. I also added PDMS, which is polydimethyl siloxane. Why did I use one weight percentage as a consistent unit for all the samples? Is because polydimethyl siloxane increases or enhances the surface wettability of the coating. Moreover, it has a SiO-Si structure, and it will actually enhance the hydrophobicity nature of the coatings. So as I mentioned earlier during the fabrication process of the graphene oxide, and also in my research objective, we wanted to see how the size of the nanoparticles actually affected the performance of the coating. Therefore, if you can note, for the 1% GO and the 3% GO, only for these two samples, I prepared two samples for the 1% and the 3% GO. And you can see one is 1% GO and the other one is 1% GO new. So one was fabricated without the influence of vacuum, and another sample, which is the new, was fabricated with the influence of vacuum. And similarly, for the highest loading ratio of 3 weight percentage GO, for this also two samples were prepared. One was without the influence of vacuum and one was with the influence of vacuum. So over here, we can actually see the difference. How does the influence of vacuum play a role to actually produce good, well-distributed, non-cluster nanoparticles? And let's look at figure 6 over here. And this is actually the coatings that were coated on the glass substrates. So if you look at the 1% GO and the 3% GO, which was fabricated without the influence of vacuum, we could see a lighter color. And you can also see that the nanoparticles were not uniformly distributed, which clearly shows that agglomeration had occurred. And there was large cluster in terms of the size of the nanoparticle, and it did not homogeneously disperse or blended or mixed well during the blendings of the coatings. So how the coatings were applied on the glass substrate as well as on the metal substrates, I used manual brushing method. Okay, so this is basically when we are using two different types of resins, this is called as a multifunctional coatings. So when we're talking about traditional coatings simply means single resin only being used. So for example, either you use just acrylic or you just use epoxy. So if when that happens, the results, or it will not produce a good barrier property for the coating. However, when we mix two separate coatings, it gives us multifunctional features, and our coatings are also thick. So when we do the manual brushing method using a brush on both sides of the metal substrates, and for the coating substrate, of course, only it's being done on one side, you can see that the coating thickness actually varied. And this is because it was done manually, which is something that cannot be controlled. So the darker texture that we can see on the 0.5 GO, the 1% GO new, 2% GO and 3% GO new, which was fabricated under the influence of vacuum, had a darker texture, which dispersed evenly, and the size of the nanoparticles were also in nanometer range. So from here itself, we know that we are expecting the results to be slightly lower for the samples that were fabricated without the influence of vacuum. So how do we ensure that the cross-linking had occurred between both the resins? So here I actually added IPDA, isophorone diamine, which was calculated based on the ratio of the epoxy. So it's basically 10:1. So if you are using 10 weight percentage of epoxy, so we use 1 weight percentage of IPDA. So that is to ensure that the cross-linking had occurred between both the resins. So for the results and discussion, let's look at the water contact angle, and let's look at figure 8. So figure 8 illustrates the water contact angle measurements for all the coatings with the inclusion of PDMS. And the first thing I would like to talk is the base. So when where I also calculated the water contact angle for the 10 weight percentage of the polymer matrix, which was acrylic to epoxy ratio. It exhibited a water contact angle of approximately 87 degrees. So it clearly shows that the base itself is not hydrophobic. So when we look at the water contact angle in figure 8 for all the samples with the inclusion of graphene oxide at different increments, values of the 2 weight percentage of the graphene oxide exhibited the highest value. Now, graphene oxide itself in nature is hydrophilic, and their values, just the graphene oxide itself, has exhibited, it was reported that the graphene oxide had exhibited a water contact angle of approximately between 60 to 70 degrees. So over here, with the inclusion of EDMS, it actually enhanced the value close to having a hydrophobic nature. So among all the samples, the 2 weight percentage graphene oxide exhibited the highest result. Okay, and another important observation that we can see over here is that the 1% GO and the 3% GO that was fabricated without the influence of vacuum exhibited the lowest water contact angle. And this actually indicated that agglomeration had occurred, and the influence of vacuum plays a critical role to ensure that the nanoparticles homogeneously dispersed within the polymer matrix. So figure 9 shows the surface characterization that was done. So for the EIS, electrochemical impedance spectroscopy, the coatings were exposed to 3.5 weight percentage NaCl, which is basically seawater conditions, over a period of 30 days, and then the corrosion protection performance of the coatings were evaluated. So basically, you place a PVC tube on the metal substrate, and then you leave it for 30 days. Okay, so let's look at figure 10. This is actually the board plots for all the coating systems after 1 day of immersion. And among all the coating systems, the 0.5 weight percentage GO exhibited the highest result up to the 30th day of immersion, as illustrated in figure 11. So this clearly indicated that and was also in line with the previously reported literatures that smaller content of the inclusion of nanoparticles were much more favorable because it could uniformly disperse within the polymer matrix. Okay. However, the lowest performance was exhibited by the red one, which was by the 1% GO that was fabricated without the influence of vacuum. And the second lowest, which was expected, was exhibited by the 3 weight percentage GO. So in other words, the green and the red, which was 1% and 3% GO, exhibited the lowest result. And this was as expected because it was fabricated without the influence of vacuum, and it had also exhibited the lowest water contact angle result. So just to just to give you the knowledge of how do we know how good are the coatings. So we look at the y-axis. So anything at 10 to the power of 4, between 10 to the power of 4 to 10 to the power of 5, the coatings are actually poor. So 10 to the power of 6 to 10 to the power of 7, in that range, it's considered moderate. However, anything above 10 to the power of 9 is considered excellent. That means it has provided excellent barrier property of the coatings to withstand the penetration of the electrolyte ions. And we can look at 0.5 up weight percentage. The values were well above 10 to the power of 9 up to 30 days of immersion. So in overall, among all the coating systems, the 0.5 weight percentage GO, which exhibited approximately 85 degrees water contact angle, was the best, was the optimum coating system, which exhibited the Z impedance value well above 10 to the power of 10. So these are the table 2 illustrates all the Z impedance values but it was at the same order of magnitude, 10 to the power of 10 as well. And we can look at the 3 weight percentage. The values were at 10 to the power of 8. And for the 1% GO that was fabricated without the influence of vacuum, there was a drop by an order of magnitude from 10 to the power of 8 to 10 to the power of 7. So now when we have already evaluated the water contact angle and the EIS, now it's very important to know whether our coatings are intact or not, whether there are any cracks, any holes, okay, and etc. So all the coatings were subjected to the crosshatch tests with respect to the ASTM D3359-17 method B standard. And we can see that A to F, which represents the 0.5 up to 3 weight percentage GO, from here we can see that A, B, C, D, and F exhibited a 5B rating. Okay, that means there were no detachment of any flakes. The surface was smooth. The coatings were intact. There were no cracks. However, for the 3 weight percentage GOE, for diagram E, we could see that there was some kind of detachment, but it was only less than 5%. So it exhibited a 4B rating. However, all the coatings did not show any kind of cracks, and they were basically intact. And the results here were supported by the EIS as well as the water contact angle. Now, let's look at the field emission scanning electron microscope, which determines the surface morphology. And again, from A to F, which represents 0.5 up to 3% GO. And here it's important to see that for A, B, C, and D, we could see that there was, for A, for example, for A, 0.5 GO, which was fabricated under the influence of vacuum, it had a uniform surface. Okay, there was no the inclusion of the nanoparticles blended very well with the polymer matrix. So for B, which is representing the 1% GO without the influence of vacuum, we could easily see that there was presence of larger nanoparticle size. And it did not blend so well within the polymer matrix. For C, 1% GO new, fabricated with the influence of vacuum, the surface was pretty much uniform. It blended very well, and it was homogeneously dispersed within the polymer matrix. For D, which is representing 2 weight percentage GO, it was pretty smooth. It actually covered all the holes that was in the coatings, and that's the reason to why it provided a tortuous path effect to delay the electrolyte ions to penetrate through the metal substrate interface. For E, which is the 3% GO fabricated without the influence of vacuum, we could see larger nanoparticle size, which was resulted due to the agglomeration phenomena. And for F, when we compare it to E, the F, which was fabricated under the influence of vacuum, there was a slight agglomeration, but it was much more better. It blended much more better compared to the inclusion of the nanoparticles that was fabricated without the influence of vacuum. So one important thing that we need to, I did as another step to verify the results was to actually calculate the lateral dimensions of the GO. So I took the highest loading, the highest concentration among all the samples, which was the 3 weight percentage GO. So for figure A, it illustrates the sample that was prepared without the influence of vacuum. And for B was the one with the influence of vacuum. And we could see that without the influence of vacuum, larger lateral dimensions were exhibited compared to B, which was slightly smaller. And this confirmed that the influence of vacuum plays a key role during the fabrication process of the graphene oxide. So the conclusion here is that among all the coating samples, the 0.5 GO exhibited optimum results. The nanoparticles were successfully fabricated using the new method. The inclusion of graphene oxide nanoparticles enabled the synthesis of thick and crack-free coating films, and they were able to withstand corrosion for a longer period of time. And the results exhibited here were in complete agreement with the novelty and similar studies that were conducted in the past. Okay. So these are some of my publications that were published with respect to the corrosion studies. Okay. And these are some of my books that were published with respect to graphene, which is my specialization. And these are some of the achievements at both international and local platforms, where I received a gold medal for various other studies. And these are the certificates that I obtained with respect to the awards, the achievements. And these are the references. So before I end my presentation, I would like to take this opportunity to thank the organizers for giving me the opportunity to participate in this Congress. Thank you so much.